So let's try to generalize the arguments that we just worked out. So let's suppose I've got some atom, and that's going to be what I'm calling the system. And then that atom can be in a certain number of energy states. So on the left, I've got energy states for the system. So the atom can be in energy E1, E2, E3, E4, any of those energy levels. And then, just like in the system we worked on, that atom is in contact with a much larger system. And in the previous example, that was the other three atoms. So this is what I'm calling the remainder. But now I want the remainder to be a big reservoir. It's going to be a reservoir at temperature T. So it's many, many atoms, not just 3 or 4, but tons and tons of atoms at some equilibrium temperature T. And I'm going to ask the same question: what is the likelihood that the atom is in any one of these particular energy levels? So let me focus on two of these states. Let me call this psi1. That's the atom in some particular state, psi1. And let me call this psi2. That's a different state that the atom can be in. The lesson that we learned on the previous couple slides is that the probability that the atom is in state 1 is going to be related to the multiplicity of the remainder of the system when the atom is in state 1. So let me just write that in words, because that's kind of the key point. So there we go. So that's what we had kind of reasoned out previously, that how likely is it that the atom is in state psi1? Well, that depends on how many ways you can arrange the rest of the atoms. And if there's more ways to arrange the rest of the atoms, leaving atom in state psi1, it's going to be more likely. That was the idea. Similarly, we could do the same thing for psi2. It's the multiplicity of the reservoir, the remaining atoms, when the atom is in state psi2. And in particular, I want to focus on this ratio for now. The ratio of the probabilities that the atom is in state psi2 divided by the probability that the atom is in state psi1 is going to be the ratio of those multiplicities of the reservoir, psi2 divided by psi1. However, now we can make a connection to entropy, because we remember that S of the reservoir will be equal to KB natural log omega of the reservoir, right? So omega of the reservoir is equal to E to the S divided by KB, entropy of the reservoir. And that means that the ratio of these multiplicities is E to the difference in entropies, S2 minus S1 divided by KB. Sorry, I decided to write that a little more clear. So S2 means the entropy of the reservoir when the atom is in state psi2. And S1 was the entropy of the reservoir when the atom is in state psi1. Okay. Okay, now this is a huge number of atoms, the reservoir. And the system is just one atom. So this is going to be a small difference. You know, doing something to that one atom is not going to change the reservoir but very much. It's going to be a small difference. So let me change that S, this change in entropy, to a ds. So E to the ds of the reservoir divided by KB. So it's a small change, infinitesimally small. Okay, so the ratio of those probabilities here is equal to E to whatever the change in the entropy of the reservoir is when the atom changes between those two states, divided by KB, Boltzmann's constant. Okay, so it doesn't seem so helpful at the moment, but we can make this a little more useful by using the laws of thermodynamics. Okay, so we've worked out this much so far, that the ratio of the probabilities that the atom is in state psi2 divided by the probability that it's in state psi1 is e to the ds of the reservoir divided by kb. And so just to remind you, what is ds for the reservoir? What I mean by that is the reservoir, the entropy of the reservoir in state, when the atom is in state psi2 minus the entropy in the reservoir when the atom is in state psi1. So one way to think about this is to imagine an atom transitioning from state 1 up to state 2 like this. So imagine the atom makes that transition. I want to know what was the change in entropy of the reservoir when the atom did that. That's what this is telling us. So to think about that, let's do the combined first and second laws of thermodynamics. So I'm going to use now, the first law is du is equal to dq minus dw. This is a review of old stuff. And then for a reversible process, I had dq was tds minus dw was pdv. But then this has to be true for any process because everything here is a state variable. So I can rewrite this, ds is equal to du over t plus p over t times dv. So what is the change in entropy of the reservoir when the atom makes this transition? It's, well, the change in energy of the reservoir when the atom makes this transition plus p over t times dv. Change in volume of the reservoir when the atom makes this transition. Now this piece is really, really small, so we can ignore this. And that's because the atom doesn't really change. I mean, when the atom absorbs a little bit of energy and goes up to a higher energy state, the volume the volume change in the atom is really, really small. It's going to be a fraction of the size of an atom, and it's just totally negligible here. Okay, so let's ignore that piece. Now let's think about what is this piece here. How much did the energy of the reservoir change? Well, energy is conserved, right? So if the atom is transitioning from this state to this state, that means some energy is coming. That energy has to come from somewhere, and it's coming from the reservoir. So some energy is going in here. The atom's absorbing some energy. And energy is conserved, so the reservoir loses some energy, the atom gains some energy, and the amount of energy that the reservoir loses is equal to the amount that the atom gains. So the change in energy of the reservoir is going to be minus the energy change of the atom, because energy is conserved. And then we know how much the energy change of the atom was, because we know it went from state 1 up to state 2. So this is minus E2 minus E1 over T. That's ds for the reservoir. And let's substitute that in now up there. So the probability that the atom is in state 2 divided by the probability that the atom is in state psi1 is e to the minus E2 minus E1 over KB times T. And if you look at this, you see that the ratio of these probabilities is the ratio of the exponentials. So another way of saying this is that the probability that the atom is in state psi n is proportional to, there might be some constant here, and there will be some constant, proportional to e to the minus en over kbt. So that's the central result what we've been trying to calculate. And this piece here, this e to the minus e over kt, is what we call the Boltzmann factor. That's really, really important. It's like one of the most central results in statistical mechanics. It says that if I want to know the probability that something is in some state when it's in contact with some reservoir at temperature T, so it's in thermal equilibrium, the probability that it's going to be in there depends on e to the minus the energy of that state divided by kt.